This question is titled, How do I make a change? And it's all about mutating data frames. How do I make a change to the contents in my data frame if, for example, I want to take a column and compute some change to that column? What is this setting with copy warning? And is this something serious? Is this something that I should try to avoid? And how does this all tie together to an objective approach for laying out the cells in my Jupyter notebook? How do I decide where one cell ends and the next cell begins? Unfortunately, in this question, we won't have an opportunity to talk about how to deal with dependent columns. There are some very sophisticated approaches that we can take using registered accessors or using object orientation and that property decorator. We also won't have an opportunity to talk about the in-place flag, what it means, why it's something that we could never really rely on, and why it's slowly being phased out. Instead, why don't we take a look at some sample data? And here we have some sample data that is sales data. And this sales data has one small addition. This sales data includes combo sales. Instead of selling individual items a la carte, you're selling them as part of a combo. What constitutes a combo may be dependent on the different store. Is that a hamburger and a french fry? Is that a hamburger, a french fry, and a milkshake? This may depend on the locality. But if we take a look at our sales data, we can see it's indexed on the day, the location, and the item. If we take a look at the unique locations, we have 3 stores that we're dealing with. If we take a look at the unique items, there are 4 items, one of which is the combo. And if we take a look at our data and we unstack the item, we get a nice looking data frame like this. For that date, for that location, each one of these columns is the amount of each item that we sold. So if we were to use the sales data as part of some sort of cost tracking, we're trying to figure out what do we need to sell these items for in order to recoup our costs. What we might need to do is take that combo column and combine it with the french fry, hamburger, and milkshake columns to get the actual number of each individual item we sold. If the combo is a french fry and a hamburger, then we sold 10 more of them than what this data represents because we need to join that column together with the other 2. Here we have some sample code. And to make our lives a little bit easier, instead of looking at the sales on a day-by-day basis, we're looking them grouped together on a location and an item basis. So we're just going to look at each location and each item in a structure that looks like this, minus the date portion, because we'll have aggregated this over the entire set of sales data, all of the months, all 90 days of sales data we have. What we're going to try to do is we're going to try to take that combo column and add it into this data, but we're going to do a little bit of filtering because it turns out in some locations we're allowed to sell a french fry, hamburger, and milkshake together as a combo. In other locations, there may be some local legislation that says we don't really want people to be buying that many milkshakes, and so try not to sell them together in a combo. The combo is just the french fry and the hamburger. And so here you can see what we're doing is we're trying to add these together. And we'll take a look at the result. But before we take a look at the result, the question I have for you is, can you spot the bug? If you took a look at this code and you said this is going to run and this is going to give you an output and it's not going to give you an exception, you're partially right. But it does give you a warning. And the warning it gives you is the setting with copy warning. What on earth does that mean? And does this actually have an effect? Is it just telling me, hey, watch out, you're setting with the copy? Or is there a material problem in my code? Well, if I remove these 2 lines that were supposed to do the work of adding the combos in, you can see that the data before and after these 2 lines are run is identical. And so, even though this code did not raise an exception, it ran to completion. That warning is a very meaningful warning. This warning told us that we thought we were changing the underlying data, but we weren't. We thought that we were taking that combo column and adding it into the french fry, hamburger, and optionally the milkshake column when we uncomment these, but in fact, no operation got performed. And so this is a big deal because you can think that we comfortably assume that the resulting values are exactly the values that we want to look at, but in fact, this warning is telling us, no, that may not be the case. In fact, it may be the case that instead you think you've added that combo in, but you're looking at the unadded values. If we take this same result and we change it very slightly to look like this, can you spot the bug? if you took a look at this code and you said, oh, we're looping over this, so we should never loop over a data frame, that's not the bug, because we're looping over the structure of this data frame. We're looping over very few entities, and those entities aren't likely to grow. So that should be fine. If you're saying that we'll get a setting with copy warning, in fact, we don't. And we, in fact, see the underlying items being updated. So it turns out that this might have been an approach that we could have used in order to address the previous problem. In fact, if we take a look at this last option here, where we do this with a slightly different approach, we use a lock with two accessors, and we ask you, can you spot the bug? Your intuition may be exactly the same. Oh, we've already fixed the bug, and in fact, there may be multiple ways to fix the bug, except here, something went totally wrong. There was, in fact, a different type of bug, and these got added in a very bizarre fashion, and we have nans all over the place, and even though there was no setting with copy warning, the data that it gave us was garbage. And so even though it may look like there may be different approaches for solving this problem, some of these approaches may be themselves buggy in their own way. So what does this all tell us? Well, if we start at the very beginning, we know there are two ways that we can talk about the data. We can say, right now we're looking at the data as a live view of some underlying information, or we're looking at the data as some copy, some snapshot in time of that underlying data. And if we were doing this in NumPy, it's generally pretty easy for us to figure out if something's going to be a view or a copy. This is going to be a view, this is going to be a copy, and this is going to be a copy. Because NumPy has some very simple rules for this. If some operation, in generality, might have to create a copy, then it always creates a copy. And you can think, if NumPy is an interpretive view of raw memory, well, what does the interpretive layer contain? It contains what type of memory that is. Is it Int64? Is that Float64? What the shape of that memory is that 3 by 3 or 1 by 9, where the location of each item is, some striding. You skip 24 bytes to get to the next row. You skip 48 bytes to get to the next column. All of that information is in that interpretive layer. If all you have to do is change that interpretive layer, then you're going to get a view. NumPy is going to say same memory, but just change the interpretation. If you might have to copy the elements over because there is no way to create an interpretive layer that is consistent with the rules of how that looks, for example, uniform striding, then there's a copy. Here, what we can think is the layout of this data. Sure, it might be 3 by 3, it might be 1 by 9. We can change the interpretive layer, but here, where we're just saying, give me 3 elements, which just tells NumPy, oh, maybe you're just going to skip all the elements, or you're going to just change the size in that interpretive layer. So you just can do a view. Here, this is asking us to perform an operation using a mask, and there's no guarantee that that mask has contiguous values. There's no guarantee that the values that are greater than 0 at some portion, and the values that are less than 0 at some other portion. And so you're going to be jumping all around this structure. This mask is going to have true and false with no discernible pattern. And because you're going to be jumping all around, there may not be a uniform striding. There may not be a way for you to say every 2 values is the value that I want to look at. It might be a value I want to look at, right next to the value I want to look at, skip 7, then a value I want to look at, then skip 3, value I want to look at. And that interpretive layer has no way to encode that. As a consequence, this must be a copy. Similarly, if we want to change the data, well, obviously, if we want to change the data in this fashion, that doesn't mean that we want to change the original data. And even if plus 0 should have no effect whatsoever, in generality, plus anything is going to require that we create a copy, and so this creates a copy. Now, if we weren't certain about that, one thing we could do is we could use numpy.sharesMemory in order to assess this for ourselves. We could ask NumPy, does x's and x's with this slicing share memory? If so, it's a view. Does it with this mask indexing? No, that must be a copy. Does it with this arithmetic operation? No, it must be a copy. There are other ways we can assess whether something is a view or a copy. We can dig down into the underscore methods on this NumPy wrapper object, and it can even tell us things like what the base object is in the case of a copy, in the case of a view, what we're actually a view of. But shares memory is a very simple way for us to assess. Do you share memory? Are you views of something, or are you copies? Another thing that we could use in order to assess whether something is an in-place operation in NumPy is a little bit of knowledge, a little bit of mechanical sympathy with how Python works, what Python is able to see. I can look at this code and I can tell you which of these are operating in place and which of these are making a copy and changing and not changing the underlying data. This is making a copy, this is working in place, this is making a copy, this is working in place. If we work backwards, this is obviously working in place. This is what the out parameter is all about. This is obviously making a copy. It doesn't tell you where the output's going to be, and maybe you want to preserve the original data where it is. Why one of these is always a copy and the other one is always in place might be a little bit harder. But if we think a little bit about what Python interpreter is capable of seeing, then it should be very obvious. The Python interpreter cannot see or does not allow you to hook into the assignment of something, but it does allow you to hook into the addition and the augmented addition of something. In other words, if we have x plus y, we can actually hook into that and customize what that means, and it's this call here. And we can hook into that distinct from x plus equals y. Because we're able to see these as distinct patterns from the perspective of the Python interpreter, that means that NumPy is able to see this distinct from this. And NumPy is able to see this distinctly enough to say, oh, you meant to change the underlying data, I'll do this in place. Versus here, NumPy cannot see that you are assigning back to the same structure. It cannot see that you intended to do this in place, and so NumPy has no choice but to first perform this operation and then rebind this data, so it has no choice but to make this a non-in-place operation, make a copy first and then an assignment. Similarly, although we don't have time to go into the vagaries of Python scoping, it's fairly straightforward once you see one or two little tricks that the parser and that the compiler do. It's often the case that people don't have a very good sense for whether a change inside a function is going to be visible outside that function. Like, for example, if I have x equals 0 outside the function and I say x equals 1 inside this function, what will be the value of x after I call this function? Does this have the ability to reach outside of this function and change this value here? Well, when we run this code, clearly not. Here, if we do something slightly different, if we say x equals x plus 1, does this have the ability to change this x out here? And if we run this code, we'll get an error, an unbound local error. And the reason for that is, inside a Python function, a variable is either always outside, i.e. global scope, or inside, i.e. local scope. It can't change from one to the other. So this can't mean take the outside x and make an inside x, take the global x and make a local x. That's not possible within Python. Additionally, Python the Python interpreter will guess at the parsing and compiling stage whether something is on the inside or the outside, and x equals is a pattern that it sees as, oh, this must be a local variable. Thus, this line says, create a local variable x using the local variable x plus 1, and you can see Python says unbound local error. You're telling me to create x using x. Unfortunately, it can't see any deeper than the superficialities of x equals something. So when it computes this, it gets confused and you get this unbound local error. If you wanted to fix this, you might have to put this little annotation here, this indication to the parser to generate a different bytecode, and then this is visible on the outside. What does confuse people sometimes is, what if you have a mutable type like a list? Here, does this append or the clear operation have the ability to change the thing on the outside? And in fact, it does. Every time I run this code, you'll see there's some change on the outside. And if I do a clear here, you'll see that's visible on the outside as well. The reason for that is this line here says, take the x that I can see, which is the one on the outside, and perform this operation in place on it. And this is key to understanding why it is that some of the approaches for avoiding the setting with copy error, or the setting with copy warning, that is, work. Here, if we take our code and we look at all of these options, some of these will cause a setting with copy warning and some won't. And we can analyze why the ones which don't, and the ones which do. What is this going to do? This is first going to look up the value for New York. And it's going to take that result and it's going to look into that result and find this particular key in that result and add one to it. This is likely to be a view of the underlying data because probably the data is on some sort of sorted index, and so this can just be a view. All of the elements are going to be in some particular striding, and this here is going to be just operating on that view, taking another view of that view, and then you can see Pandas is going to be able to see, oh, you want to change this view, which changes the underlying data. Is that guaranteed to be the case? Well, it's a little bit hard for us to really get a good sense for it. So even though this may work, we may choose to avoid it. Similarly, if we do this the other way around, we can try and reason about it the same way, but probably we should avoid these. Instead, we might prefer syntax that looks like this, because this is very clear. Here we're saying take the original object and perform a lookup on that original object. Pandas can see we're looking up both a row indexer and a column indexer, and Pandas can see, oh, we want to mutate that in place. So this is quite unambiguous in terms of going and changing the underlying data. This may even be our strong preference for what we want to do versus either of the above. Now, if we do this with a mask, what we can think is the mask is not necessarily going to be contiguous. And just like with that NumPy end array, because it's not going to be contiguous, this is going to create some kind of copy. So it's going to create some kind of view. This is going to create some kind of copy. And this operation is going to set on that copy, which will not set on the original data. Thus, we get the setting with copy warning, and we won't see the original data changed. Whereas here, this will actually work. And this will go to the original data, subject to that mask, and change it. The problem with the variation of this that we looked at before was that the index alignment was off. What we are adding to this structure didn't have an appropriate indexing, and Pandas was trying to match things up, and that's where we saw an error. We will talk about index alignment more, but let's talk about your layout of your Jupyter Notebook. And here I have a very simple Jupyter Notebook with 2 cells. I do the data creation in one cell, and I do some data manipulation in another cell. I add to one of these columns. This is a bad idea. And it's tied to our idea of where and when we change things very closely. Because think about this. When you're doing these changes to this data frame, it's not just the setting with copy warning that you want to avoid. You also want to avoid problems that arise when people use this structure, or use this notebook rather, the way in which people use notebooks. How do you actually use a notebook that was emailed to you? You do that run all to run everything from top to bottom. Then you go and you play around in one cell and you rerun that cell. Maybe you run some cells above, maybe you run some cells below. You do this very non-linear, so you jump around. And you'll run a cell, and sometimes you'll say, wait, did I run that 1 time? Did I run that 2 times? Or did I run that 3 times? Or did I run that 4 times? Consider that if you ran this cell here 6 times in a row, the result is going to be meaningfully different than if you ran it 7 times in a row. It'll have changed the data 6 times, not 7. And your ability to understand what the code is going to do next is going to be dependent on you knowing exactly the number of times you ran this cell, which you probably don't. You don't remember, oh, did I run this yet? Did I not run this yet? Whatever the case may be. If you were to write these 2 pieces in one cell together, the problem is eliminated. Because every time you run the cell, you reconstruct the data, and then you perform the mutation. So these cells can always be run in an idempotent fashion. Every time you run the cell, you get the same result. So your ability to reason about this is greatly increased. In general, what you should think about a cell in your Jupyter Notebook is, can somebody using my notebook run these cells without having to overly concern themselves with the order in which the cells were run, without having to overly concern themselves with how many times each cell was run? Are these cells self-contained, and are they idempotent? Does running them 2 times in a row give the same result and have the same consequence as running it once in a row? Because you can never remember, did I enter twice or did I enter once? And if you enter twice and that gives you a materially different result, then this is going to be a very difficult notebook to work with. These kind of assignments are not something that you have to avoid. You just want to avoid them if they are isolated, because if they're isolated all by themselves, then every time you run that, you're going to change that structure, and that might then require, if you want to reset yourself to a known state, rerunning some previous cells, and then it gets really messy. In general, one of the things you can think about is people like in Jupyter to write, and people like with Pandas, to write these very long chained operations. And is there a real benefit to writing this over writing this? I don't think so. I don't think there's a huge benefit unless the latter helps guide somebody to what lines of code cannot be separated, what must be atomic. When you see these very long chained operations, one of the benefits of those long chained operations is that it is very clear that this should not be broken into two cells, that these take you from some known working state to some other known working state, where all of the intermediaries, they're still being computed, and all of those temporaries are still being created. But it is unlikely that somebody will interleave some other code or split this into two cells, because it's pretty clear that these are all the steps necessary to take you from some working state to another working state. That's where I see that this particular style is useful, and that's where I see all of these super long chained operations or may actually be beneficial in your life, because otherwise I would never tell you, just jam everything onto one line, jam everything into one expression. Does that really gain us value in our life? No. Now, as a coda, I want to share with you how I would solve the original problem if I didn't want to first group it by month, but instead I wanted to do this on a day-by-day basis. How do I fold in that combo information on a day-by-day basis using everything that I've seen? I'm going to write one large chained expression subject to the same thinking that I had before, and you're going to see that it's a couple more steps involved, and hopefully I'll be able to motivate for you why those extra steps may be valuable, why those extra steps may be useful, because I will solve this problem with a little bit more generality than how it was being solved previously. What I'm going to do is I'm going to start with my sales data. And it looks like this: the date, location, the item, and how much of that item. I'm going to unstack the item so I get each one of these items as a column. You can see the combo, the french fry, and the hamburger. I'm going to fill value at 0. So if, for example, some location didn't sell any combos or any french fries on that day, it gets filled with a 0. The next thing I'm going to do is I'm going to do a transformation of this data frame. And I'm going to transform this data frame to re-index it. I don't know if there are missing days. I don't know if there are missing locations. Maybe some location was shut down for a weekend, and I want to make sure that this data is consistent. So what I'm going to do is I'm going to re-index it. And the way I'm going to re-index it is I'm going to construct a new index that takes every possible day and every possible location, and then re-indexes filling with 0. And that way I know I'm guaranteed to now have these two indices be contiguous and complete, and I might do a sort index at the very end to make sure they're in sorted order as well. Now that I've guaranteed that, now that I know every single day for my date range exists, every single location exists, and each one of these has a particular column, then I can do something very nice. What I'm going to do is I'm going to do another data transformation. And in this data transformation, what I'm going to do is I'm going to start by taking the cities where I do the full combos, Chicago and New York, and I'm going to pull out the french fry, hamburger, and milkshake from those. I'm going to take that together with the cities where I don't do the full combo, where it's just the french fries and the hamburger, and I'm going to concatenate these together. And you can think, okay, what's the purpose of that? Well, in the case of the latter, I'm going to fill that milkshake column with 0. So now I come back to what the original data looked like, but I've segmented it, and in the non-full combo, I just have a 0. So here, this represents how much of combo french fries, how much hamburger and milkshake you sold. I'm going to take that, and I'm going to rename these columns to indicate that these columns are how many french fries I sold as part of a combo, how many hamburgers I sold as part of a combo, how many milkshakes I sold as part of a combo. I'm going to take that together with the original data, and in the original data, I'm going to mark my original sales as solo sales. So now, notice, I haven't removed any data, I haven't mutated any data, I've just tacked on additional supplementary columns. I have how many french fries were sold as part of a combo versus how many french fries were sold as part of just a solo a la carte entree option. I'll change my indexing slightly to make this a multi-indexing on the columns, and now this is very useful because I can answer very nice questions like how many hamburgers were sold as part of a combo, how many hamburgers were sold solo, how many hamburgers were sold in total. And I'll do just a little bit of cleanup here just to name those two layers. And so this is the type of order that you have in each item. And with that, I'm ready to go. I'll sort my index just to make any subsequent operations fast. And if somebody came to me and they asked me, tell me how much we sold in total, combo or not, I don't care about the distinction, then That question can be answered with just one line of additional code, a group by, just group by the name of the item and sum them. Other questions can be solved. What if it changed somewhere in the middle of the month? What I want to look at or what these criteria are? Well, that would constitute just a very small change either to this layer here or a very small change to my projection and my final computation. Here you can see I haven't deleted or removed any information. I've just taken my original data frame and I filled out additional information. And now I can answer a lot of really sophisticated questions from this result. It took me a couple of steps, took me quite a bit of jargon, but I'm in a really nice place to be able to answer every question without having thrown away any of the original data. So, what do we do about this? Well, we need to develop some mechanical sympathy with Python and Pandas. It comes up over and over. In order to use this tool, we do not need to be at the level of the core developer of the tool, but we need to generally understand what the tool likes, what the tool doesn't like, what works well and what doesn't work, because this tends to affect all of these other considerations, like is something a copy, is something a view, was something done in place or not. More specifically, we want to avoid mutating our data frame. We will prefer creating additional computed columns because it's safer in general, and it's something which allows us to avoid things like the setting with copy warning entirely. Instead of setting that original data frame, just create a subordinate column. And then when you want to, for example, use what you would have done originally with that setting with copy warning, well, just take that as subordinate column directly or take that as an arithmetic computation with the existing columns. If we are a Jupyter Notebook user, we want to arrange our Jupyter Notebooks to make it easy for other people to use. So we want to split cells up where those cells are repeatable, where they're idempotent, and where there are a minimized set of dependencies between this cell has to run first before this next cell has to run, and where you can rerun cells any number of times and the result is still valid. There are qualifications here. You can't do this exactly if it's the case that some of those cells are very time-consuming. You may want to split off a cell that is very time-consuming, that doesn't represent a complete view of or a complete loading of some data. You might want to say, oh, do the loading that's slow here, and then put a comment and say, please, every time you do this reloading, please run this cell afterwards, immediately after. But if that cell afterwards is doing all the transformation and it's not slow, try to keep all of the transformation steps in the same cell together, just so that, yes, you can't rerun one cell all by itself. You can run two cells with a comment telling you to do that, but you've at least made somebody's life easier. These are our general guidelines for what happens when we want to work with data frames and we want to mutate them. Try not to. And if you're going to do them, at least try and do them together in such a way where you can't result in cases where people are scratching their head trying to figure out what went wrong or what's going on here. Our next question is titled, how do I line them up? And this question is about index alignment. It's about broadcasting. What are the rules of broadcasting in NumPy? What are the rules of index alignment? What do I need to be aware of? Unfortunately, we won't have an opportunity to talk about the rules of index alignment on multi-indices, nor will we be able to talk in too much depth about things like the matrix multiplication and some of how that generalizes and some of the rules of its index alignment, although we've included some of this material for you. Let's take a look at our sample data. Here, we have our pricing data, how much each element is, or how much each item that we're selling is sold for, and we have some information about our costs, how much it costs us to produce each one of these items. And together with our pricing data, we could see what our profit is on a combo basis, what our profit is on a per item basis. And we could use this as part of some of our financial forecasting. Using this data together, what we're going to try and do is we're going to try and figure out what is our price per location, what is our combo price per location. And we're going to do this with these two lines. The first one will tell us French fries in each location. The next one will do some sort of multiply and then sum to tell us, oh, all three of them purchased together in that location would be this. Can you spot the bug? If you told me that the bug is that there's some misalignment here, that you're going to get a matrix not aligned error, you're exactly right. This operation doesn't work. There's an index alignment problem. If you told me this operation won't work as well, but it won't error out on you, it'll just give you a bunch of nans, which is definitely wrong, even though it didn't raise an exception, you're absolutely right. Both of these are index alignment problems. This one's much more visible in that it will create an exception. This one, less visible until you look at the result, in which case, oh my goodness, that is definitely not what I was looking for, a bunch of nans. What's going on here? Well, what you might think is maybe I need to transpose one of these sides to make it work, but clearly if I transpose one of these sides, it doesn't work. It only works if I transpose the other side. And surprisingly enough, if I swap the arguments for my combos, this does seem to work. So that's a little perplexing. Here we have another example with just some random data from NumPy. Can you spot the bug? If you said that this first operation will work perfectly fine, it'll give us exactly the result that we want, it'll be a 3 by 4 by 5 matrix, you're exactly right. If you said this second operation will fail and we'll get a broadcasting error, you're also exactly right. We cannot add x's and z's, they do not broadcast together. If we wanted to fix this, what we might have to do is x's plus y's is already correct, but for x's and zs, we might have to reshape zs, so we could reshape it in this fashion, or we could reshape it using this indexing with new axis. Both of them are completely fine ways for us to solve this problem, but we have to do something in order to make x's and zs broadcast. What does this tell us? Well, NumPy defines all arithmetic and comparison operations between NumPy and D arrays in terms of some rules, and we call these broadcasting rules. In general, there's no such thing as scalar addition or scalar multiplication in NumPy. Instead, what we do is we always do like-by-like operations. We always take a 3 by 3 structure and we multiply it or add it or compare it against another 3 by 3 structure. But if the other argument is not 3 by 3, we have to figure out how to change that argument. We have to figure out how to repeat it along one of its axes so that we can have an exact like-to-like match. When you think about a scalar, well, that's pretty obvious. If you took a 3 by 3 matrix and you added 1 to it, well, how do you make 1 match the shape of a 3 by 3? Well, you repeat it 3 here and you repeat it 3 here and you make it a matrix that's 3 by 3, all containing 1s. Then you can do exact to exact, exact to exact, exact to exact operations. That's basically what broadcasting does. That's basically what happens behind the scenes. In the case of pandas, however, we define all arithmetic and comparison operations between pandas series and data frame in terms of index alignment rules. And the index alignment rules are slightly different, and there's 1 or 2 small catches, but it's basically the same idea as broadcasting, some rules for defining how these objects interact. In other words, here we have x's and y's. If we add them together, they're both 1 by 3 or 3 by 1, whichever way we want to look at them. So we just take the elements at the 0 index, the elements at the 1 index, the elements at the 2 index, and we just add them up. If we do x's times 3, this doesn't do a scalar multiplication. It creates a structure that looks like this, 3, 3, 3, and then it multiplies that element-wise against x's. Now, whether it exactly does that or not is somewhat secondary. That's really an implementation question. What we can think is conceptually that's what's happening. And this is part of why we see things like NumPy scalars pop up. Because what's happening behind the scenes is NumPy wants to treat everything as a non-scalar value, as some sort of broadcastable or dimensioned structure. Here are the rules for broadcasting, and they're pretty straightforward. What you do is you look at the shape of the 2 arguments. You take those shapes and you right align them. So you match up the rightmost dimension against the rightmost dimension. And then you work right to left. And you try and match them up. And there are 2 cases in which you can proceed because you have a match. Either the dimensions are identical, you have 3 against 3, or one of them is 1, or one of them is shorter than the other. Think about this. If you had a 3 by 3 structure against a 1 by 3 structure, well, if you line them up, 3, 3, 1, 3, the 3's match, and then you have 3 against 1. Well, this just means you have to take this structure and repeat it 3 times on that particular axis. That's how broadcasting works. If this was a 2 by 3, and there's a 3 here and a 2 here, well, how do you line that up? You're not going to do some, greatest common divisor, least common denominator type situation. That would be a little bit odd. And so you need to do some sort of mechanics to make that work. Maybe you need to explicitly repeat one of them 2 times and explicitly repeat the other one 3 times. The automatic broadcasting rules don't do this for you. That's what that reshaping was all about and why that made it work. That's what that fancy indexing with the new axis was all about. That's what made this work. In other words, if I wanted to take x's and y's and I wanted to add them or multiply them or compare them, you can see they already line up. What's going to happen with y's is it's going to be repeated 3 times on this axis. A missing dimension just is the same thing as a dimension of 1. And in fact, if you think about it, any structure can always be given an additional dimension of 1. You could say this is a 3 by 3 matrix, or you could say this is a 3 by 3 by 1 cube, or you could say this is a 3 by 3 by 1 hypercube. You're not really changing the data, you're just adding layers, you're just embedding it in a larger space. If we took a look at x's against zs, however, they don't line up. And this is why we get that broadcasting error. The 5 against the 4, the 3 against the 4 do not line up. What we probably wanted to do is we probably want to repeat it on the outermost axis. So what we probably want to do is reshape it to add a 1 here. So that's why that reshape works. Or to do the exact same thing using a new axis operation. Or if we really wanted to, we could do that exact same thing using an explicit tile or repeat, but we'd have to do another reshape there because tile and repeat won't add in new axes. The tile or repeat will just repeat something on an axis. You'll have to pull that out to a new axis. That's how broadcasting works. If we wanted to debug our broadcasting and really see what's happening behind the scenes, NumPy provides us with a broadcast to operation. And so we can see what y's looks like broadcast to x's. Here, this is what y's looks like broadcast x's. You can see where the repetition is. It's block by block by block repeated. So you can see what that means to repeat it over a particular axis. If you wanted to see the same for zs, you can see how zs gets repeated, and you can see it's a different type of repetition. You can see it seems to be repeating in this direction. And this is generally what you can do if you want to really figure out what the element by element operation is going to look like. Look at the original data, look at the other data, broadcast them to each other's shape to see what the resulting shape is going to be, and then just eyeball and say, oh, you're going to take that 0.19 in the top left-hand corner against something in the top left-hand corner of the other, and you're going to match these up exactly. Pandas index alignment works slightly differently. Here, with a non-multi-index, there are 3 separate things to consider. Series against series is an exact match on the index. Data frame against data frame is an exact match on the index and the columns. Series against data frame is matching the index of the series against the column of the data frame, except there is one caveat if there is duplication. So here, we're only going to talk about, for the moment, non-multi-index unique column, the unique values in the index or the columns. In other words, if we have a series that has these values, indexed on A, B, and C, and another one that has these values indexed on B, C, and D, the addition of these two things just matches the A against nothing, so you get an AND value, the B against the B, the C against the C, and the D against nothing, so you get another NAND value. If we had 2 data frames, A, B, C, B, C, D on the column, so there's a little bit of overlap, W, X, Y on the index, X, Y, Z on the index, so there's a little bit of overlap. So if we look at these, we'll see, okay, that's what one looks like. That's what the other looks like. If we sum these, everything where there is no overlap will be NAND out. Everything there is an overlap will just match exact to exact. Pretty straightforward. If we did series against data frame, that's where there's a little bit of a hitch. What we do with the series against data frame is we take the index of the series against the columns of the data frame. And so visually that kind of makes sense because you can see ABC, these are the columns of this data frame defined here. ABC, these are the index of this data frame, the rows of this data frame, the rows of this series defined here. And DF against S1. Here's DF, that's S1. They'll align exactly as you expect. A against A, B against B, C against C. If it were the case that you took S2, however, and in S2 you have something that you want to align the index of one against the index of the other, well, you can't, so you have to transpose one of these. But if you transpose S2, it doesn't make a difference. You know, transposing is about swapping the indices in the columns, but a series doesn't have columns. So you could transpose this to your heart's content. It will not change this. You have to transpose the data frame. I have to transpose the data frame to make this work. Otherwise, it will still give you a result, but that result is going to be nonsense because you can see it tried to fill in the overlap, but it took. These are the values in the index of the series. It thought those were supposed to be columns. There was no overlap, and it fills the whole thing with NaN. Now, unfortunately, we do not have time to talk too much about what the matrix or scalar product does, but we have this in a little bit of the notes and a couple of examples. For the most part, you can think of this as an index aligned operation plus some reduction, rows against columns. And the order of these operations will matter. X's against Y's will make a difference against Y's versus X's. In a similar sense, you'll see the same thing for the Pandas data frame and the Pandas series. But rather than go into those details, there's one important thing for us to discuss. What happens if the index values are non-unique? Because there's one little catch here. Here, we have a couple of structures, and we can see whether their index values are sorted and whether they are non-unique. In a couple of these cases, there are duplicates. You can see the double A or the triple A. And when we add these up, you're going to see some interesting behavior. If we add up S2 against S3, where they both have non-unique indices, it just matches them up like against like. The A against the A, the A against the A, the B against the B, the C against the C. Except if we make a very small change, we change the ordering of these so they have distinct or non-identical ordering, it will compute a Cartesian product. Here, Pandas says, I don't know which A is supposed to be which A and which B A is, and the other one's supposed to be which A, so I'm going to give you every A in the first against every A in the second. And so you see this, when you have non-unique indices and they don't have the same ordering, you will get a product, you'll get more rows, which means doing that sort index operation might have a dramatic material effect on your data, because if I do a sort index here and a sort index here, I get a different number of rows than if I didn't do the sort index here. It has a material change to my computation. If it's the case that one of these has more values of A than the other, you can see we're again seeing some non-exact match of the indices, and as a consequence, we're getting a Cartesian product, and that will be the case if I'm doing S1, S2, or S3 against S4. If these indices do have duplicates and they are not exactly matched up to each other, the same ordering with the same counts of everything, then we're going to start getting Cartesian products, and it's something to watch out for, because this may be a case where a group by and a sort index may be necessary to just make sure that your data is normalized so you don't end up getting more rows than you expect as a consequence of some computation. And if it's the case that you try and do the same thing with the data frame, it'll occur on both the rows and the columns of the data frame. Here you can see a Cartesian product on the columns and the Cartesian product on the rows, because these two original structures had duplicates and they weren't identical to each other. So what do we do all about this? The most important thing when you're working with Pandas is don't forget about the index. Pay close attention to what your indexing is. Pay close attention to what your columns are. Only do a reset index if it's for some deliberate reason. If you genuinely want to change that index by popping off a level, or you generally want to throw away that index, reset index is fine, but otherwise, avoid doing just automatic reflexive reset index just to try and get something working, because oftentimes it won't actually solve your problem, it'll make your problem worse. Similarly, if you look at a structure and it has a range index, really think, is the most interesting thing about this data that I can number it from 0 up to some number? If not, that range index is going to require that you end up recapitulating all the mechanics of the index yourself, but it's going to be clumsier, harder to read, slower, and you're going to end up with the same sort of problem that you have. If you want to do some group bys and sort indices every time you do some data loading, just to normalize that data, just to make sure you avoid some of this weirdness of this Cartesian product, that I think is completely reasonable. At the worst case, you waste a little bit of computation, but you did make sure that, for example, index values are unique. You did make sure, for example, that index values are sorted identically. Whenever you perform arithmetic operations on Pandas data frames, Pandas series, or NumPy and D arrays, you need to think in terms of the respective rules. For NumPy, think in terms of broadcasting. Look at the shapes. If the shapes match up exactly, there's nothing to worry about. It's just going to do an element by element comparison or arithmetic operation. If they don't match up exactly, the broadcasting rules will help you define whether NumPy can automatically broadcast, i.e. repeat one against the other. Follow the broadcasting rules by right aligning and then moving right to left, looking for an exact match, for one of them to be shorter than the other, or for there to be a 1. If not, use reshape, use repeat, use tile, use new axis, any one of those to get them to line up. And you can use broadcast 2 if you can't visualize the results too easily. If you're not quite sure what that repetition would look like, use broadcast 2 to debug. When you're using Pandas, make sure you know whether the left-hand side and the right-hand side are data frames or series, because that will affect how the broadcasting operates. So be careful about whether you're working with series or data frames. Try and be precise about that. Look at the index and the columns of each structure. You may need to do a transpose if it's a series and a data frame to get them match, or maybe in a data frame against a data frame. If you happen to be using multi-indices, make sure everything is correctly named. Because what the multi-index can do is it can align portions, it can align levels of that index, but it does it by matching them up on the names that you gave them. This is why you'll see in my code I use rename axis all the time, just in case I later need to do an index-aligned operation on a multi-index and I want it to line things up. And be aware of what happens if your index or columns are non-unique and they're dissimilar. They're dissimilarly ordered is one case where this will pop up, or they're not identical to each other is another case where they'll pop up. For example, you have more A's in one and fewer A's in the other. With that, that should give you the core rules of index alignment. For the most part, index alignment is something that just kind of sits in the back of your head, comes to the forefront every time you're doing an arithmetic operation. If you have structured your data frame and your series correctly, it's not something that you really worry about that much. But you set things up nicely, and then you get the benefits of them, solving multiple simultaneous operations instead of one narrow one, and making use of all of what Pandas has to offer. Whatever the case may be, in Pandas, the one piece of advice I can give you is don't forget about the index. This question is titled, Is this helping? And in this question, we'll talk about Pandas, NumPy, Xarray. We'll talk about how to pick the best tool to really help you solve the problems you want to solve. We'll talk about the difference between the built-in collection types, the NumPy and D-array, the Pandas series, and the data frame, and we'll talk about Xarray. Unfortunately, we won't have an opportunity to talk about what happens if we need something that looks kind of like a NumPy and D-array and also looks like a list, like something that grows. What is a Pandas array? We won't have an opportunity to talk much about what a Pandas we won't have an opportunity to talk much about what a Xarray data set is, and we won't have an opportunity to talk about things like the NumPy structured D type, which starts to look sort of like a cut-down version of a Pandas data frame. We also won't have an opportunity to talk about really interesting tools like awkward array, which solve a problem which NumPy by itself cannot solve. Let's take a look at an example. Here I have some code that takes a two-dimensional list, and we'll say that this represents an image, and these are pixel values. And we want to figure out what the mean pixel is for the entire structure. So we do this using the statistics module to compute the mean of the mean. Can you spot the bug? If you said the code works exactly as we expect, you're correct. If you said the bug is not in the code itself, but it's in the comment, because there is no such thing as a two-dimensional list. Lists are always one-dimensional, you're absolutely right. And if you said maybe there is some appropriateness of data structure here, maybe this should have been a NumPy and D array or an Xarray data array, you're absolutely right. This probably shouldn't have been a list, but fundamentally, I think the most concerning is there is no such thing, and there will never be such thing as a two-dimensional list. This is a nested list. This is a list of lists. Here we have some image represented as a Pandas data frame, and we're again computing the mean pixel value. Can you spot the bug? If you said this isn't quite the most appropriate data type that we might use, probably a NumPy and D array or an Xarray data array is a better choice for this. I agree with you completely. That might be a bug. If you said that this comment here is also incorrect, because there is no such thing as a two-dimensional Pandas data frame. Pandas data frames are like indexed one-dimensional structures, even though the documentation might, for lack of a better term, call these two-dimensional structures. I think you're right. But largely, the code itself still works. Here, we have an example that uses a NumPy and D array. Can you spot the bug? If you said this code works, the comment is correct. There are two-dimensional NumPy and D arrays. I mean, it's n-dimensional. Of course, there are two-dimensional structures, and there is, in fact, no bug here. I think you're correct. And for bonus, if you said this, however, is correct but might be a little bit clumsy, you should instead use Xarray. That's, I think, worth a little bit of a bonus point. What does this all tell us? it turns out we have a couple of choices for data structure, each specific to the kind of problem we want to solve. We have things like the Python list, which is a collection of high-level elements, and we use it for program structuring. It's ordered, it's one-dimensional, but we can nest it. We have the NumPy and array, which is a low-level computational type, and it's n-dimensional. And in fact, it's some interpreted layers to memory, so it's arbitrary, or it's free for us to change what we view this data as in terms of its dimensionality. We could look at a 2 by 3 by 4 structure, or a 2 by 12 structure, or a 1 by 24 structure, and that's just a change to the interpretive layer. Doesn't require that we change the underlying data. If we move over to pandas, we have the pandas array, which is a low-level piece of data. It's an indirection between probably a raw NumPy and array. It's used for computation. It's one-dimensional. There is no nesting. We probably won't use it that much directly. If we look at pandas, we have the pandas index, which is the mechanism for identifying the physical position given a human label within some data. It's one-dimensional. You can't nest it, but you could layer it. There could be levels, for example, with the pandas multi-index. The two that we tend to work with in pandas, the series, well, series is just a pandas array together with a pandas index. So a pandas series is one-dimensional. There's no nesting, and it's a low-level computational type. And the pandas data frame, which is basically two pandas index, one on the rows and one on the columns, and some opaque data storage, a block manager. And there's really no nesting there, but instead of being two-dimensional, it does have two coordinates. We might more precisely say it is like indexed one-dimensional. It's a collection of one-dimensional data sets that have a similar indexing. Let's take a look. Here we have a Python list. This is not a two-dimensional list, because how can you have a two-dimensional list where this dimension has 3 elements and this has 4 and this seems to have 1 more element? No, it's a nested list. There is arbitrary nesting, and we can have lists within lists within lists at any arbitrary point, at any arbitrary depth. We can append to this structure to our heart's content. We can clear this structure, and generally, any code that we write using the structure should be correct, irrespective of how much we nested, irrespective of how many elements there are. If this is an appropriate way for us to view this data, then the code that we write is going to be able to work with this data, even if we append more things, even if we nest more things, as long as we're nesting it within some coherent understanding of what this data represents. In other words, we can change the size of the data without having to change the code. Here, we have a NumPy and array stored within a Python list. And we couldn't store this in one single NumPy and array, because here this is a 3 by 3 layer, and this is a 3 by 3 layer, and this is a 4 by 4 layer. And we couldn't store those together because we wouldn't be able to come up with a uniform striding. NumPy and arrays are n-dimensional, which means there are some axes, some dimensions, and those dimensions have a fixed size with them. It is 3 by 3 by 3, not 3 by 3, except sometimes one of these is a little bit longer and sticks out the end. Where we might use NumPy together with pandas is here. This image, this single image, represents the pure computational element that we operate on, whereas this list represents the human understanding of the problem we're trying to solve. You have 3 images that you've loaded from 3 separate files that might be completely dissimilar to each other, but you want to loop over them and do something consistently with each element, compute the mean. And so, in general, what we can think is NumPy and pandas are our core computational types. They are at the core of our computation, but the rest of Python sits outside of that to give us program structuring, to show us how it is that a human being thinks about the process of manipulating those core computational elements. If we have 2 Python lists and we add them, we see concatenation. And that makes complete sense, because if this is a program structuring element, then taking 2 things which we're going to loop over and do something with and adding them just means loop over all 6 of them. Loop over all of the elements. That makes sense. Whereas if we try the same thing with the NumPy and array, it adds them using those broadcasting rules, which makes sense because it's a core computation element. Then generally we want to express these operations in terms of that computation, which is some mathematical vector addition view of this. If we look deeper at our NumPy and array, we can see it is an interpretive view of raw memory. We can see what the interpreted type of this is. We can see where the underlying data is. One of the consequences is we cannot resize that NumPy and array in place, because we don't know what sits after it and we don't know what sits before it. So if we need to grow this thing, we'll need to copy all the data over to a new structure. We have to explicitly do something like an H stack, a V stack, a D stack, a concatenate, or an array operation, whatever the case may be. We have to explicitly invoke that copying. It will not grow by itself behind the scenes. There's no pre-allocation, there's no capacity, any of that kind of stuff. As a consequence, we use pure Python for data that's growing, but we tend to use NumPy for data that is already been collected, that's ready for analysis. And it's tricky for us to work with data as it grows within NumPy. If we have this NumPy and D array and we want to operate on it, we can operate on it. We can say, give me the element at 0, 2. We can say, give me the mean of these down the axis 0. Give me the mean of these down the axis 1. But if you looked at these two operations and you said, wait, which one's axis 0 and which one's axis 1 again? Is it going this way? Is it going this way? Well, that's a common confusion. And in fact, what we see in pure NumPy code is quite a few magic numbers. And you might wonder, what's so bad about magic numbers? After all, they're magical. Well, the incantation necessary to remember exactly which magic number is axis equals 0, axis equals 1, may sometimes be beyond the capabilities of our mortal memory. And so what we might say is that NumPy, what we might call an unnamed tensor, is not particularly ergonomic, not particularly friendly for a human being to use, because you have to remember what these axis numbers are, and you have to know how those correspond to the layout of your data. And when you try to do things like build libraries or build functions on top of NumPy, well, then everybody has to know, wait, which axis corresponds to which aspect of the underlying data? Are we all consistent? Are we dealing with it in the same way? If you give me latitude and longitude data, how do I make sure it's latitude, longitude, not longitude, latitude? And that can lead to confusion. Thus, we might reach for a tool like Xarray, which you can think of as a superficial API wrapping over a NumPy and D array. Xarray contains no compiled code, and it extends NumPy using Pandas indices, but it extends NumPy to give you the ability to refer to the different axes, different dimensions by name. And this is a very powerful thing. Even though the wrapping itself is in pure Python and relatively superficial, the capabilities that it unlocks are quite powerful. Let me show you what I mean. Here we have our image in our NumPy and D array, but we've notated what dimensions this has as an X dimension and a Y dimension. And we've notated the coordinate system. This is no longer 3 pixels 0, 1, 2, 3 pixels 0, 1, 2. It's now pixels that have been captured on some coordinate system, for example, a human measuring system. If we had a detector, this might be at 0 centimeters, at 5 centimeters, and at 10 centimeters. And these two do not have to be evenly spaced. These two do not have to be identical. They can represent some human understanding of what these underlying values actually mean in terms of their location. We can do all the things that we could do on a NumPy and D array, like do the mean on each axis, or we can do these means by using the names. We can say, give me the mean over the X dimension, give me the mean over the Y dimension, and when you look at that, it should be a lot easier to understand what that means. You can select elements. Oh, select X values 0 and 10. Okay, I can really see what that's saying. Or give me values 0, 2, and 5 interpolated with the linear interpolation if the underlying data doesn't happen to exist. This is where Xarray is very powerful. What you can think is behind the scenes, it's just taking NumPy, Pandas, and SciPy, but giving you a really nice API to invoke all of these in a human understandable fashion. This idea of labeling data is the core idea behind the Pandas index. Here, we have a series, and it contains 3 values. I don't want to talk about values at position 0, 1, and 2. I want to talk about values as they were collected. I want to talk about values at day 1, day 2, and day 3 as of some specific date. Pandas gives me both capabilities. Using the iloc accessor, I can look up the element at position 0. But using the loc accessor or indexer, I can look up the position at the human label, the first of the year. The index is the mechanism that sits between these two. The index is what allows me to translate a human description of a position to a physical machine description of a position. And in fact, I can ask this index, give me the physical location of the data corresponding to the human label, the first of the year. If I have a Pandas data frame, it's the same idea, but instead of looking at just the rows of this structure, instead of looking at just one element, I'm looking at two indexers, two coordinates to access one value, which is why you might see in the pandas documentation it calls pandas two-dimensional, because there's two coordinates to refer to one element. But the underlying storage of this data is not guaranteed to be one contiguous two-dimensional structure. In fact, it's obscured from us how this is stored, and conceptually, this is not two-dimensional data. Let me show you what I mean. Here, I have some complex sales data. And in that complex sales data, I have the revenue, the expenses, who the manager of that franchise was, and who the manager of that store was, and whether or not for that particular quarter and for that particular location, it was a franchise location or maybe a non-franchise, maybe it was a corporate-owned location. This block of data here is not two-dimensional, and I'll prove it to you. For two-dimensional data like an image, you can look at any arbitrary diagonal and it makes sense. You can rotate it arbitrarily and it doesn't really change the data. Here, the only meaningful operations that you're going to perform are either straight down the columns or straight across the rows. You're never going to perform an operation down that diagonal. That would be meaningless. How do you take the revenue from one row with the expenses of the other row, with the manager from the third row, and then the franchise from the fourth row? Doesn't make any sense. Similarly, this is clearly heterogeneous data. This is not a two-dimensional structure with just numbers. This is, in fact, four distinct measurements. One measurement of the revenue, one measurement of the expenses, which just happen to be in the same units, but they might not necessarily be in the same units. One measurement of the manager and one measurement of the franchise, and they just happen to be four measurements that share the same indexing, that share the same labeling of their entities, and we've brought them together as a data set. This is what a pandas data frame is. It's not really two-dimensional data. It is like indexed one-dimensional data. You're working with these one-dimensional columns that just happen to have been lined up nicely so you can do operations down the columns or across the rows. But if you needed real two-dimensional data, you want to use NumPy or Xarray. If you needed higher order dimensional data, 3 and 4-dimensional, definitely don't use NumPy for this. So definitely don't use pandas for this. Use NumPy or Xarray. So what do we do with this information? Well, it's important in our programs to distinguish between program structure and computation. Program structuring means how does that program actually do something a human being cares about? Program structuring usually occurs on a human scale. So usually when you're talking about program structuring, you're talking about 5 images, 50 images, 500 images, 30 days, 500 days. Whereas computation usually occurs on a scale of data, and there can be very distinct computations. Give me this analysis for the last 500 days. That's within a human scale. I know how many days 500 days is. I've lived 500 days. For 5 trillion data elements, I don't think I can count as high as 5 trillion. There's very distinct scales here. When I talk to you about the data, I can say, oh, this is for days 1, 2, and 3, but I don't really say for data item 1, 2, and 3. I just assume that there's some amount of data that might be very large or even larger, but the size of that isn't really related to the structuring of how I'm describing this. Now, there's a lot of overlap in the middle between what constitutes program structuring and computation, and that's where these tools become very difficult to use, where it's not clear whether this is program structure or computation. You have to do some very sophisticated things to bridge that gap, but it is not unusual for there to be, in simple programs at least, a very clear distinction between these two. When you deal with program structuring, you're dealing with pure Python, and that's really where you want to live. When you're dealing with computation, you're dealing with NumPy, Pandas, Xarray, and that's really where you want to live. For program structuring, use the Python built-in types, your lists, your dictionaries, your tuples, your frozen sets, your sets. Everything will work out just nicely because those types work well for human-scale data. But when you deal with computational work, when the scale of the data is billions of elements, trillions of elements, those pure Python types will not be sufficient, so you need to reach for your high-performance data types, your NumPy and DArray, your Pandas data frames, or wrappers on top of that, your Xarray data array, your Xarray data set. If your data is one-dimensional, you have a couple of choices. A Pandas series, a Pandas array, a NumPy and DArray are all fine choices. If your data is n-dimensional, you no longer have the same set of choices. If your data is n-dimensional, and really n-dimensional, especially if it's n greater than 2, like 3, 4, 5-dimensional data, NumPy and DArray or an Xarray data array. Largely, the Xarray data array is just a wrapping of the NumPy and DArray, so it's going to be NumPy and DArrays anyway. If your data is one-dimensional, but you have a couple of them and they all have the same indexing, that's not two-dimensional, that's like indexed one-dimensional, that's a Pandas data frame. If your data needs human labeling, then you're going to want to use Pandas or Xarray. If your data is just a mathematical matrix, and you say, oh, row 0, row 1, row 2, that's all I need to ever say about my data, use pure NumPy. But if you need to say, oh, the measurement at 2 centimeters, the measurement at 4 centimeters, the measurement as of some particular day, the measurement at such and such frequency, that human labeling requires some interpretation in your code between how the human being talks about the data and how the data is actually laid out. You want a Pandas index or a Pandas index in columns. Whatever the case may be, you want a Pandas series or a Pandas data frame for one-dimensional data or an Xarray data array for 2 or higher dimensional data. If you want very fine-grained control over memory usage, well, unfortunately, Pandas doesn't really give that to you. Pandas obscures a lot of how the memory usage and where copies are made. And so if you really need fine-grained control over memory usage, you don't really have a choice but to use pure NumPy or maybe NumPy with some Xarray. And if your transformations that you're going to perform are transformations that are only meaningful in specific on what you might call flat data, typically data that has more rows than it has columns, data that is not two-dimensional but like indexed one-dimensional, things like melts, pivots, stacks, and unstacks, well, then you want to use Pandas. With that said, I think you have a good set of guidances and a good checklist to go down every time you think about the problems you want to solve, and this should allow you to use not only Pandas, not only NumPy, but all of these together where appropriate.